Um, Back in chapter 1, where I covered vector spaces, back then I was only talking about pure vectors, n-tuples, ordered lists of numbers, vectors. And I said a vector space back then had just two axioms, the closure axioms of addition and scalar multiplication. We could get away with that because vectors already came with defined operations and some other things. Well, smart people came up with kind of a set of critical axioms to characterize a generalized vector space. I'm going to include the closure axioms. In this case, it's this I and VI 6, 1 and 6. Those are the closure axioms. And by the way, not all textbooks include them in this list of axioms because they could be derived from the other 8. If it satisfies the other 8, it's going to be closed. But I'm going to keep them in there because a lot of times those are the easiest things to check. And we'll talk about that in a minute. But if you look at what a lot of these things are, like here it just says addition is commutative. That was the case with the vectors we talked about, and associative. And there's such a thing as a zero and an additive inverse. These are things that our standard vectors already came with. And I'm not going to go through all these. We're not going to go check each one every time. Let's see. What about all unit vectors in two-dimensional space? Those are all the vectors with a magnitude of 1, right? Well, there's certainly a subset of R2. But if you multiply by any scalar not equal to 1, you go outside the set. It's no longer a unit vector. So that particular example, that's not a subset. It doesn't pass the scalar multiple closure. You can also note there's no 0 in it. If there were a 0, it wouldn't be a unit vector. So it also doesn't satisfy this axiom. We didn't necessarily have to check the closure axiom, but to me, that was the easier one to check. I'm not going to go through it, but if you just think about matrices of a given size, they obey all these axioms. You got addition, you got scalar multiplication, addition is commutative, yada, 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 there's the 0. It satisfies all these. So the vector space, all matrices of any particular size. You can't mix and match. You can't have 3x3s with 3x4s in the same vector space. You can't even add them. You could have non-standard operations. Who says plus means what we normally think of arithmetic plus, addition? I'm not going to go through this in too much detail, but the barred symbols mean the members of the set we're talking about. So X bar just means a normal X, but only the positive reals. Same with the Y bar. But addition, this operation doesn't mean normal arithmetic addition. It means take these two numbers, which will be positive numbers, and multiply. And scalar multiplication doesn't really mean the normal multiplication. It means take this real number, positive real number, and raise it to the power k. The additive inverse really means 1 over x. And the 0 identity, the thing we call 0 in this set, really means 1 in normal numbers. So it can be very weird. We redefined operations. But if you go through all the axioms, that set obeys all the axioms. It's a vector space. That's why you got to define what you mean by these operations. And kind of why we did that when we talked about vectors and then matrices. You define operations any way you want. So there's a whole bunch of things that are legitimate vector spaces. They obey all those axioms. All the set of all real numbers, any dimension of those things, meaning R2 and 3D vectors or n-tuples, all those, any matrices of a given size, but also the set of all polynomials, or the set of polynomials of degree less than or equal to some given n, a set of real valued functions defined on the entire real world. We're not going to go through all those axioms, but they're vector space. I'll break this up into two videos because it's getting kind of long.